All right, our next stop on our nervous system journey is an action potential. So we've just finished going over what a graded potential is. And so we had those EPSPs that make it more likely that an action potential is going to happen, and the IPSPs that make it less likely. And we know that summation can come together and pull that membrane potential up to threshold. So this slideshow goes through what happens once that membrane potential hits threshold. The terms that you're going to either need to know or will go over during this slideshow include graded potential, resting membrane potential, stimulus, threshold, voltage-gated channels, depolarization, repolarization, hyperpolarization, the sodium-potassium pump, and the refractory period. So we'll go over these, or probably mention all of these in the next few slides. So an action potential starts when a neuron reaches threshold. Before threshold, the neuron's at the resting state, that resting membrane potential of negative 70 millivolts. Threshold is negative 55 millivolts. And then the next step after that is depolarization. After depolarization comes repolarization, hyperpolarization, or the refractory period, and then the neuron returns to the resting state. So we're going to go through all these steps now and learn how all those ion channels that we've been talking about come together in this action potential. Here's a key to the symbols that I use in this video. The leakage channels, which remember are always open, are light blue and light purple. The voltage-gated channels are dark blue and dark purple, and this over here is closed, and this is open. And then we have our sodium-potassium pump. The color code for our ions: sodium is blue, chloride is yellow, potassium is purple, and the protein anions that we find inside the cell are orange. At resting membrane potential, sodium moves into the cell and potassium moves out of the cell through leakage channels. Okay, and so that is moving down its concentration gradient from high concentration to low concentration. While this is occurring, the sodium-potassium pump is still working, pumping 3 sodiums out for every 2 potassium ions going in. So these two types of channels work together to maintain that resting membrane potential. So when the neuron hits that negative 55 millivolts, reaching threshold, that triggers the opening of the sodium voltage-gated channels and the potassium voltage-gated channels. But the sodium channels open really quick, and the potassium channels open very slowly, like one of those doors in a horror movie. So because those sodium channels open quickly, the sodium ions are the first to move, and they move from the extracellular space to the intracellular space. They move inside the cell. And it happens relatively quickly and reverses the charge of the cell on the inside and the outside. So these ions right here are going to be rushing in, okay? And it's going to reverse this charge. So this part is going to become negative, and this part is going to become positive. So let's just look at what that looks like on the graph. So here on the y-axis we have voltage, and here we have time. And so at this point we're at resting membrane potential, information's coming in and out, and we finally get a strong enough stimulus to hit threshold. Once you hit threshold, those sodium channels open up and the sodium starts rushing inside the cell. And it's going to go all the way up to this positive 30. Once we get to the top of that graph, those really slow potassium channels have finally opened. And at that point, the sodium channels actually close because of these inactivation gates that sodium channels have. So you see here the bottom of these sodium channels is closed. The top is still a bit open, but nothing's getting through. But now we have the potassium channels are open and potassium is rushing out of the cell. Okay, here the charge becomes negative again inside the cell because it's losing the positive potassium charges, but the ion concentration is still off, right? There's more potassium outside the cell and more sodium inside the cell. What that looks like on the graph is here's repolarization happening. Get my pen going. Here's repolarization happening. And again, those potassium channels are slow, so they come down here and they go below resting membrane potential. Okay, they become hyperpolarized. Okay, so once again, so here is resting membrane potential, threshold gets reached because of enough stimulus hitting the cell, and the cell depolarizes because the sodium channels are open and sodium's rushing inside the cell. We get to this top of this crest, and that is when the sodium inactivation gates close and the potassium gates have finally opened, and potassium goes rushing out of the cell, and it's going to be moving down both its concentration gradient and its electrical gradient, right? Because it's moving towards the negative, okay? So the potassium's moving outside of the cell, and so much potassium moves outside of the cell that we get back to that positive charge on the outside and that negative charge on the inside. But now what's causing the positive charge on the outside is all the potassium that we have, and what's causing the negative charge on the inside, still proteins. Nothing new there. Okay, and so because those potassium gated, voltage gated channels stay open for so long, the cell goes below resting membrane potential into this hyperpolarized state. So that just means that the difference between the inside and the outside of the cell is even bigger than when the cell is at rest. Okay? So in between the repolarization and the hyperpolarization is this area called the refractory period. And a neuron has an absolute refractory period and a relative refractory period. And the refractory period is a time when it's either impossible or very, very hard to generate another action potential. So the absolute refractory period happens right here when those sodium inactivation gates close. Those gates stay closed until right around here. Okay, so that area right here is the absolute refractory period. There's no chance of another action potential happening because no sodium can go through the gates. Down here, where it's hyperpolarized, the sodium inactivation gates are open, and the potassium voltage gates are still open. Remember, they're very slow to close, but it's so far below threshold that it needs a huge stimulus to have another action potential. So that means either very, very rapid action potentials coming from a postsynaptic neuron, or just lots and lots of signals coming from many, many neurons. In order to return back to having more sodium on the outside and more potassium on the inside, we have to use our friend, the sodium-potassium pump. And so the sodium-potassium pump, remember, it requires ATP, but because it requires ATP, it has the power to force sodium up its concentration gradient and outside of the cell, and same with potassium, except for it's going to force potassium back inside the cell. So 3 sodium go out for every 2 potassium coming in. And that's going to reestablish the proper ionic gradient. So, or the proper ionic concentrations between inside and outside the cell. So here's a much prettier graph than the ones that I've been drawing. And I just want to go through these. So here, right here is that resting membrane potential. Sometimes you get a stimulus that's not big enough and you don't get an action potential. So these are those failed stimuli. But if we're lucky, we hit threshold. The sodium channels are going to open up. Sodium's going to rush inside the cell. And that's going to depolarize the cell membrane. It's going to decrease the difference between the inside and the outside of the cell. Okay? Right around here is when the sodium inactivation gates close. So no sodium can go through the voltage-gated channels anymore. And those really slow potassium gates have finally opened up. So when those potassium gates open up, the potassium goes rushing out of the cell, and that causes repolarization. Okay? The repolarization continues, and we get to negative 70 millivolts, which is that resting membrane potential, but those potassium gates are so slow that they stay open. But it's right around here that the inactivation gates open up again, okay? And the voltage-gated sodium channels are kind of reset. So this area where it's hyperpolarized is called the relative refractory period. This period, it takes a really strong stimulus in order to get an action potential. From here to here is the absolute refractory period. Because of those inactivation gates, we can't get another action potential. So once we get here, right, we're back to the inside of the cell being negative and the outside of the cell being positive, but we have more potassium outside the cell and more sodium inside the cell. So what returns us to our normal resting state with not only the correct charge, but also ions in the proper places is the sodium-potassium pump. But if it were only the sodium-potassium pump, at some point we'd have only sodium ions outside and only potassium ions inside. So fortunately, the sodium-potassium pump and the leakage channels work together, kind of balancing each other out. So the leakage channels are going to allow sodium to go down its concentration gradient from outside to inside, and the sodium-potassium pump is going to pump those sodiums back up the concentration gradient. And on potassium side, the leakage channels are going to allow it to go down the concentration gradient outside of the cell, and the sodium-potassium pump is going to pump potassium back inside the cell. I hope this video helps clarify questions that you have on action potentials. Please post your questions to the Community Help Forum if you have a thing that I didn't answer here. Take care.